Welcome back. So now we're moving on to another kind of storage system. The goal is also to store data in there, but it's a bit different. I will explain how. So we've looked at relational databases, right, to store the data. We've looked into, we did the brush up 2 weeks ago. We looked into scaling out, the idea of having thousands of machines rather than one single big machine. We've seen that we can have cloud storage services, in particular object stores, that allow you to store objects that can be as large as 5 terabytes associated with keys, the key being a bucket ID plus an object ID. Key value stores, very briefly, again, that's not part of the material, but they exist. It's just that the objects are a bit smaller and the system is a bit faster. And the typical use case for these storage services is for, in the case of data sets, for storing data sets. Now, a good thing to know is that sometimes the data set you store is the raw data set. For example, you've collided a few protons at CERN, and you have a petabyte data set that you need to put somewhere. Came from scientific experiments or sensors, or imagine your Meteo Schweiz and have your temperature and pressure measures that have there. This is raw data, and you can put it in there as logs in the system. And then there is derived data. Derived data means that you consumed the raw data with some data analytics system. We will see a bit later with MapReduce, Spark, and so on. And you have analyzed the data and then produced some output. That is also data. But that data is derived. It's no longer the original data. And typically what people do is that they also store that derived data that was spit out by Spark or MapReduce. They store it right back to S3, or as we will see, a distributed file system or Azure Blob Storage. So this is for raw data and for derived data. What does it mean? It means that we will not only want to upload data and read it, we also want to be able to write back data to the system after we have created new insights from a system. But here's the thing, there's big data and big data. And a very high-level way of saying what I want to say today and contrasting object storage with distributed file system is that sometimes you can have a huge amount of large files, and sometimes you can have a large amount of huge files. That's the case of object storage. You can have billions of terabyte files, a huge number. This is a worldwide service for billions of people storing all of their data, pictures, videos in there. That's object storage. File storage, distributed file systems, as we will now look at them, is about millions of petabytes files. Very costly, right? So you might have a bit less. It will not scale up to having as many files as you would have in object storage, so a bit less. But the size of the files is no longer limited by these 5 terabyte limits. Right? You can go beyond 5 terabytes. You can even have files that are larger on what fits on a single machine, and that's no problem at all. How it works, I will explain to you. All right? So this is the contrast here, billions of terabytes files versus millions of petabytes files. More exactly, if you want to be even more exact here, I'm simplifying, I should even have said billions of files up to a few terabytes and millions of files up to a few petabytes, right? It's the upper limit I'm talking about. So what is on the left, we have already done it. It's the key value model, not to be confused with key value stores. The key value model, it's this idea of having keys as you associate with objects. And object storage that we've done last time. Today, we look at a different way with a file system and block storage instead of object storage. So now we are going to be focusing on the right part of the slide today. It all started, this is where I feel old now, it all started 20 years ago, almost 20 years ago. When the large companies started having such amounts of data that they needed a way to manage it. And so the Google file system, Google FS, was created in order to fix this. And the idea of the system back then is that when you store your data on a single drive on your laptop, it could fail. Most of the time it doesn't, but maybe once in a while you could have a failure on the hard drive, and then that's why it's important to back up and you lose everything. But the thing is, if you have a data center, it's not just that it might fail, it's that it will fail. In fact, it fails all the time. In fact, in data centers, there are people hired full-time to run over the cluster and replace everything that fails, right? It's just the everyday life of a data center is that you keep having things that fail. You need to replace the hard drives, you need to replace the servers, and so on. So it means that the way to think about it completely changes the way you build the system, right? If you have to deal with permanent failure, all the time you have things that fail in there. So it means that the way that this file system was built is that you need a way to monitor what's going on, to detect error, to automatically notice when a hard drive has crashed. And then you can build the system in a way that it automatically recovers from these crashes. That if a hard drive fails, that's totally okay. The system continues to work. That's automatic recovery. And on the highest level, if you achieve that, you have fault tolerance. Fault tolerance is this ability of a system to continue working normally, even if something's crashing or failing inside of it, right? That's called fault tolerance. So you have to imagine, if you want a visual, a data center in which people are running around 24/7 replacing crashing hard drives, but the customers outside, they don't see any of this. They see a system that just works, right? Sounds like magic, right? But it's possible to actually build these things. Okay, so there are a few assumptions. Whenever you build a system like this, so this is the requirements, you make a few compromises, right? You cannot have everything. On your hard drive, for example, if you use a spreadsheet software or a word processor, you can click on save at any time, right? And you can write and read to and from the hard drive permanently. This is called random access. This ability that on your laptops and on your smartphone, you can always read and write anything that is in your memory or on your disk. But we don't have that, and we don't want to have that in these distributed file systems. We don't care about random access and efficiently accessing any few bits at any place. Instead, what we are interested in is scanning the data. You take a file and you go through it bit by bit and scan it. This is in fact what we love to do in data analytics. This is how we'll use MapReduce, Spark, and so on. It's all about scanning the data, reading the entirety of a data set, scanning through the file bit by bit. As opposed to random access, where you might have a terabyte file, but you only want to read the bit right here, or you want to write a few bits right there, that would be random access. Who gets the difference? All right. So the system that we are building now will be optimized for scanning. We want to scan through the data. For reading and writing, we just want to have a scanning process. What we also want to support is appending. That's also fine. You already have a file and you just want to expand it at the end. You want to expand it. Think of a log, for example. You keep logging new things always at the end. That's called appending. In the original versions, these systems could not do it, but now today they are able to append at the end of a file. That's also very convenient when you create data or when you analyze data and keep creating new data. You want to be able to append it at the end. Okay, appending is not only actually suitable for when you create new data, derived data, it's also suitable for the raw data. For example, imagine that you have your Meteo Schweiz and you have your temperature and pressure sensors all over the country. You want to keep right every second the current temperature and pressure at every location in Switzerland. You can do it by appending at the end of a log. You keep appending the new measurements of temperature and pressure in there, right? So that can be used for this, can be used for a website. I don't know if you have in mind the Apache server, also creates that kind of logs and so on. All right, so we scan and we append. Another requirement of our system is that unlike your hard drive where you're the only person working on it, or your home drive where maybe there's your family, so maybe 5, 6, 7 people that are accessing it. We want for hundreds of people to be able to access the system at the same time. So this is a stronger requirement. We want it to scale in some way. And we don't want any trouble. We don't want to have concurrent access that would lead to inconsistent data, right? So if somebody is writing at some place, we need to make sure that there's nobody else who is writing at the same place. So this is another requirement. And finally, we have a requirement in performance, and that has to do with throughput and latency. We basically want a system where data flows around. The bits are flowing around. So we want a system where the limitation is the throughput, right? We are limited by the throughput and the amounts of bits that move around every second. We do not want to be limited by latency. Latency means that you spend most of your time waiting. And I'll explain to you what it means in terms of blocks. Why am I expressing it in that way? Like, this is a weird way of saying things, right? We want to be limited, but, right? We want to be limited by throughputs, and we do not want to be limited by latency. The reason why we put things that way is, as we will see in a few weeks, whatever system you have, a software on your computer, a website, it's always limited by something, and moreover, it's always limited by one thing. That one thing could be the memory that is limiting it. That one thing could be the data sent over the network that is not fast enough. The limitation could be the speed at which you read from the hard drive, or the limitation could be that your CPU is not fast enough. That's called the bottleneck. Every system has one bottleneck. Could be the CPU, the memory, the network, or the drive access. In that case, the bottleneck that we want to be in a normal functioning system, a normal functioning distributed file system, is the throughput, right? We want to be limited by the throughput, not by the latency. And again, the casual way of putting it, we just want the bits to flow around, dense around being sent back and forth. To give you a visual of what it would mean if we were bound by latency instead, that would be a system in which nothing much happens. The bits are not really flowing around, we're just waiting. We are waiting, for example, for the drives to rotate and reach the correct location below the reading head, or we're waiting for the bits to happen in some place. But this would be awful. That's not a way to analyze data. If you want to analyze data, you need the bits to flow, right? So it's a casual way of putting it, but that's the idea. For whom does that make sense? All right, very good. But you'll get a feeling for that once I have shown you the distributed file system. It will be clear. We have a question on the chat. So the streaming. So this is a good question. There are two types of systems that you can look at basically when you start dealing with data. Here we just store the data. There are two types of systems, the batch processing systems and the streaming system, right? There's examples of both. We are a bit more focused on the batch processing systems in this lecture. However, one way to answer your question is that if you look at this, scan the file, this is compatible with streaming because you can have a stream of bits that gets written to a file just like this sequentially. So this works with streaming, but it's not trivial. And in 2 or 3 weeks, so when we look at Bigtable, I will show you the magic of this. How can we manage in a system that is bound by throughput? How do we still manage to also stream in some way and support updates? But this is a cliffhanger that I leave as a mystery for in a few weeks that we'll get back to. Does it make sense? I assume yes. All right. Yeah. All right. Thank you. Okay. Now, this is to put in this context what I'm telling you about capacity, throughput, latency. You might remember that. We saw that capacity increased enormously, but the speed at which we can read it didn't. So we need to parallelize, right? And typically what limits us is the throughput. If we parallelize more, we get more throughput, but this will be our limiting factor. The second limiting factor, latency. The way it's solved is with batch processing, but this again, I leave for in a few weeks. We will discuss this more in details with HBase and Bigtable, right? So the focus today will be more on latency, on the throughput and the parallelization. Okay, now I told you about Google File System, Google FS, but this is proprietary. And what happened is that a few years later, some people created an open source version of the same, and they called it Hadoop. It's named after this little elephant, yellow elephant teddy bear, that was the teddy bear of the son of Doug Cutting, who created Hadoop. So this is for the story. And it dates back to 2006, so that's already 18 years ago. So Hadoop is made of 3 parts that correspond to the Google File System. That's already 21 years ago, MapReduce 20 years ago, Bigtable 18 years ago, and Hadoop copied that over as all the 3 parts to HDFS, the Hadoop Distributed File System, which we are covering today, MapReduce, which we are covering in a few weeks, and HBase, which we are also covering in a few weeks. So all of that we'll look at in due time. This is called Hadoop together, but we're focusing today on HDFS, all right? Just to show you how it evolved, most of the action actually happened between 2006 and 2016. This is where the whole thing kept scaling up and up and up and up and up. The location where this was done, the whole Hadoop, was at Yahoo, who is a search engine. So they needed that kind of technology to, for example, to index the web and index all the data. So you see that it went from almost 200 computers. This is the number of machines here that you had. So you had a cluster of 200 computers in 2006. And we suspect that in November 2016, that they reached something like 100,000 computers, which is the upper bound of a data center, what you fit in a single data center. That corresponds to 600 petabytes of data. What happened after that, I'll say a few words in a few weeks, but since we are at the limit of a data center, we are kind of stuck now at what we can do in a single data center. And then the only solution is to start building things across data centers, right? But for today, we are stopping at the limit of a single data center, right? So 100,000 machines maximum. Now, what am I going to do? Well, we are going to take a break. Right after the break, I will start with the model of the distributed file system. You remember what I told you. Almost every week, I do things in exactly the same way. I'll first tell you the logical model of things, the easy part, basically, how it works on the high level, and then I'll tell you about the implementation. I did the same thing with S3. I told you the model of S3, which is bucket ID plus object ID gives you an object, and that's it. That's a flat key value model. Well, I'll tell you about the model for the distributed file systems, and in particular, the Hadoop distributed file system right after the break. So I'll see you in 15 minutes. Thank you.